Hi guys, welcome to our second video in chapter 18. In this video, I'm going to cover section 18.2, which is factors affecting chemical equilibrium. So two objectives for this video. We want to talk about various factors and how they affect chemical equilibrium. And then we want to talk about Le Chatelier's principle and how it applies to equilibrium systems. Okay. So in the last video, we looked at specific equilibrium positions, right? The relative amounts of products and reactants, and we learned that it's based on factors other than the equilibrium constant itself. Some factors that it can depend on are our initial concentrations of reactants and products, our temperature of the reaction, our pressure, the presence of catalysts, changes in the concentrations of reactants and products, like if I'm extracting out my product, right? So all of these things can have a factor on the equilibrium. Okay, they can have they play a role in the equilibrium. They'll decide where exactly is our reaction sitting at equilibrium. Okay, and so the thing the principle we want to remember for this this idea of how chemical equilibrium is affected is called Le Chatelier's principle, right? And the idea is that if a stress is applied to a system at equilibrium, the system will shift in the direction that relieves that stress. Okay, and so this is going to guide us through this entire lesson here. We're going to focus on this principle. So I want to start by talking about changes in concentration and really looking at how a change in concentration will affect our reaction. Okay. And so here the idea right here, when a system experiences a change in concentration, the reaction will shift in a way that alleviates the change uh, that was made. So if we increase our reactant, we'll favor the forward reaction. So I actually have that pictured up here in the top right. We can see if we have this reaction happening where blue dots combine with black to form orange and white dots. If we suddenly increase the amount of black dots that we have, if we put in more reactant, then we are going to favor the formation of product, or the reaction is said to shift to the right. And we favor our forward reaction. So when we reestablish equilibrium, you can see that we've ended with more product than we started with before we added our extra reactant. We've shifted our reaction that way. I actually have less of my blue dots at the second equilibrium because some of them have been used up by the forward reaction. Okay. Likewise, increasing the concentration of my product favors the reverse reaction. Okay. Or if I maybe decrease the concentration of my reactant, that's again going to favor the formation of my reactant. So let's say I have that same setup, but now I remove all of my black dots. Well, what's going to happen is some of our product is going to go through the reverse reaction to form more black dots. Okay. And so the reaction then is said to shift to the left, or the reverse reaction will be favored. Okay. So at equilibrium, I will end with an extra blue dot, and now I have a black dot that reformed. Okay. So again, concentration. When I increase the concentration of something, I favor the reaction that gets rid of that thing. If I decrease the concentration of something, I favor the reaction that forms that thing. So that's the two ways that concentration will affect a system at equilibrium. And so we can use this to our advantage by dumping a ton of reactant into a reaction, and we'll strongly favor the formation of our product. Okay. All right, continue on here. We can, of course, also change pressure or volume. Now, if we have a system that has gaseous products or reactants, this will play a role, right? Pressure only really makes sense when we're talking about gases. So as long as we have a gas, pressure and volume changes will matter. Now, in the reaction that I have in this example, you can see that one molecule of A is forming two molecules of B. Okay, so that is the reaction that I have set up here. Now, and both are gaseous, you can see. Now, if I have 10 moles of gas in 3 liters, right? I have a 3-liter volume. If I increase the pressure and I squeeze that volume down and I decrease my volume, well, suddenly now I have more pressure and I have less volume. This is going to favor the reaction that gets rid of gases because that's going to reduce the pressure. It's going to alleviate the pressure. And so because my reactant side has only 1 mole of gas and my product side has 2 moles of gas, increasing the pressure will favor the reverse reaction. it will favor the formation of my reactant, okay? And so that's what we see. It says it produces less gas molecules, which is what we actually see. So again, when I have a gaseous product, if I increase the pressure, that will favor the formation of less gas particles, whichever way, forward or reverse, whichever way produces less gas particles. Okay. Temperature is an interesting one, right? Temperature, of course, is going to change our equilibrium position as well as our equilibrium constant. Now, just a quick reminder, when we were talking about changes in pressure and volume, the equilibrium constant was the same. And when we changed the concentrations, again, our equilibrium constant is the same. But now, once we're changing temperature, we can actually change that equilibrium constant, okay? And virtually every reaction is endo or exothermic, which means that we need to consider heat as either a product or a reactant in our reaction. And we'll see how it affects our reaction. So let's look at our idea of A plus B goes to C plus D. Again, it's at equilibrium because we have the double-sided arrow. And this is said to be a negative delta H, meaning this is an exothermic reaction. So it's releasing heat. So what I could do if I wanted to get crafty, I could say plus heat. Like writing with my mouse is bad, but anyway, plus heat there, right? I could say that is also a product. Okay. Now, if I increase the temperature, that means that I am adding, right? Heat is over here. Heat is a product. I'm adding more product. That is going to favor the formation of my reactants, right? Which of course will be an endothermic process. The reverse of an exothermic process is an endothermic process. So increasing the temperature here would actually favor the formation of my reactants. Likewise, if I decrease my temperature, well, it's like I'm reducing the concentration of a product now. So if I decrease my temperature, I'll favor the exothermic process or that forward reaction for this setup, okay? Another example to put some real chemicals here, if we look at the formation of methane from carbon monoxide and hydrogen gas, it forms methane in water. This is an exothermic process. So in this example, if I were to add heat, if I were to heat up this reaction, I would actually favor the formation of my my reactants, my reverse reaction. If I heat this up, it would favor the formation of the reverse reaction. But if I cooled it down, then it would favor the formation of my products. If I were to cool it down, it would shift my reaction to the right. Okay. All right. So that's temperature. Now we also should talk a little bit about, of course, biological equilibrium. You know very well that you live in a state of dynamic balance called homeostasis, right? And our body acts in myriad ways to maintain that equilibrium. One very relevant example to our study of chemistry is the equilibrium that exists between hemoglobin and oxygen in the blood. So we have oxygen that's free, and then we have aqueous hemoglobin. That hemoglobin is in a state where it is in equilibrium with a hemoglobin bound to an oxygen. And so what happens is oxygen from our lungs can dissolve and attach to that hemoglobin. That hemoglobin can then move through the body. That red blood cell can move through the body, and it can then release that oxygen into an oxygen poor environment, right? It would be able to release that oxygen. Again, it's a state of balance, a state of dynamic equilibrium here. All right, guys, that's all I had for this video. Thank you for listening. I'll see you in the next one.